Hey folks, it's Mr. C, and I am currently in Olanchito, Mexico, but I'm actually filming from Galveston, Texas. And this is lesson 67. It's a familiar topic and yet kind of a new topic. You'll see what I mean in a second. We're dealing with areas under a curve. So let's say I said, here is a curve. All right, what curve is that? Yep, it's y equals the square root of x. And if I said find the area under the curve from, say, 0 to 25, right? If I said find this area, how would you do that? What would you set up? That's right, set up an integral. So area is equal to definite integral from x equals 0 to x equals 25 of f of x dx. And what's f of x in this case? Yeah, square roots of x. No problem. You get that. Notice you have x limits of integration, an integrand in terms of x, and the differential dx. So everything's in x dx. All right, let's evaluate this real quick. We evaluate this integral, we will get, this is x to the 1/2, so you're going to have 2/3 x to the 3/2 evaluated from x equals 0 to x equals 25. All right, which is the same as you could always bring the constant 2/3 out, in which case you're going to get 25 to the 3/2 minus 0 to the 3/2. Great. 25 to the 3/2. That's like 25 to the 1/2 to the 3rd power. So what's 25 to the 1/2? 5 to the 3rd power, 125. Okay, what's 125 minus 0? 125, what's 125 times 2? 250. So we have 250 over 3. Now we're dealing with area, right? Area. So what should the units be? Units squared. Good. What if we change this problem up a little bit? And I said to you, you know what? I'd really like you to get a different area for me. I'd like you to get me the area from y equals 0 to y equals 5 between the curve and the y-axis. So I'd be asking you to get this area right here. Do you see that? Okay. This is very unfamiliar to you. Taking areas under curves is familiar to you. The process here is going to be the same, but what's not familiar to you is thinking in terms of y. You're used to thinking in terms of x. Okay, so watch. I'm taking the area under this curve, y equals square roots of x, but in y, what do we call that? We call that x equals y squared. Right? If I squared this top equation, I would get x equals y squared. All right, so this function now is x equals y squared. It's really a relation, because that's really the relation that kind of goes like this, right? But all right, let's do this thing. So we want to take the area under the curve from y equals 0 to y equals 5 of f of y dy. I know, it feels a little weird. Limits of integration are in y, integrands in terms of y, and the differential is dy. Everything is y dy. Okay, so this is the same as the integral from y equals 0 to y equals 5 of y squared dy. Now we integrate. No problem. You get 1/3 y cubed evaluated from y equals 0 to y equals 5. And pull out the 1/3. You get 5 cubed minus 0 cubed, which is, of course, 125 over 3 unit. 125 over 3 units squared. All right. How do we know that what we got was correct? Well, what if we did this? This is just a check. We're done with our work at this point. But if we wanted to check, see this rectangle right here? You can easily calculate its area. This is base times height. A base of 25 and a height of 5. Okay, so the area of the rectangle is just 25 times 5 which is 125 square units. All right. Well, here we have 250 thirds. Here we have 125 thirds. If we put those together, we get 375 thirds. 375 thirds is the same as 125 units squared. So in other words, if I add up the black area right here plus the red area right here, I get the total area, this total blue area right here. All right, this is the new material then today. Can you take the area under a curve thinking in terms of y dy? All right, look with me for a second because this might feel weird. Look at this guy right here. X equals y squared. We're thinking in terms of y. So how would you think about this? You might think about this as f of y is equal to y squared. Therefore, x is what? It's the nickname for f of y. All right, folks, so let's take this problem at the bottom of the screen. Find the area of the region completely enclosed by the y-axis and the graph of x equals 1 minus y squared. All right, folks, so let's try this example. Find the area of the region completely enclosed by the y-axis and the graph of x equals 1 minus y squared. All right, no problem. Create your Cartesian coordinate plane. Now you got to drop 1 minus y squared down. Well, what does that look like? Well, do you know what x equals y squared looks like yet? Looks like this. So what does x equal negative y squared look like? Well, it would look like that. And what do you think x equals 1 minus y squared look like? That whole thing shifted over to the right by 1, something like that. So this is the graph that we're looking at. All right, so we have our sideways parabola, x equals 1 minus y squared. Understand x is just a nickname for what? F of y. This is f of y equals 1 minus y squared. You got to learn to think that way. Okay, what's this ordered pair right here? 1, 0. And we're asked to find the area between this curve and the y-axis. This curve and the y-axis. What's the equation of the y-axis? X equals 0. That's right. So the area we're trying to find is the area between the curve and the y-axis. The area under the curve in the y direction, not the x direction. Fun. Here, let's do this thing. The area of this shape is going to be the definite integral from y equals something to y equals something else of f of y dy. What are these y limits of integration going to be? Well, you can kind of see them right here, right? There's a y limit of integration, a y limit of integration, but how do we figure out what those are? Well, we'll notice they're both along this line x equals 0, aren't they? So they both have this common issue that x has to equal 0 there. So take your equation, x equals 1 minus y squared, and set x equal to 0 and solve for y. And then you'll have your y limits of integration. So y squared is equal to 1, or y is equal to plus or minus the square root of 1 or plus or minus 1. There we go. 1, negative 1. All right, let's plug this in. Negative 1, 1. All right, definite integral from y equals negative 1 to y equals 1 of f of y. What was f of y again? Yep, 1 minus y squared dy. And now we just integrate. What's the antiderivative of 1 minus y squared? It is y minus 1/3 y cubed, evaluated from y equals negative 1 to y equals 1. Now I'm going to be very careful as I write this out here. I don't want to make any mistakes, so I'll kind of set up the difference, right? First part of the fundamental theorem of calculus. And I'm going to say this is 1 minus 1/3 1 cubed, negative 1 minus 1/3 negative 1 cubed. All right, so 1 minus 1/3 is 2/3 minus, and I'll be very careful here, Got -1 cubed, which is -1 times -1/3, which is 1/3. -1 is -2/3. Which means my area under the curve is 4/3 units squared. Very important that I made sure all my signs were correct. I'm very pedantic about it, but to make sure you get a right answer, not something ridiculous like 0 units squared. All right, so let's just review what we did. We wanted to get an area under a curve defined in terms of y dy, a curve in terms of y, the area between that and the y-axis. So the area between a curve called x equals 1 minus y squared and x equals 0. Getting the area under the curve in the y direction. So everything, my limits of integration are in terms of y, my integrands in terms of y, and my differentials in terms of y. And then I'll get an area, 4/3 units squared. Good, let's try another example then. All right, last example. Consider the area of the region completely bounded by the graphs of x equals 3 minus y squared and y equals x minus 1. Well, hopefully you recognize this now as a sideways parabola, and this is a what? A linear function. Okay, so let's graph this thing and get its area in terms of y. I'm assuming that's what we're going to have to do. Let's find out. Make a Cartesian coordinate plane. Label it appropriately. Now here we go. Let's graph x equals 3 minus y squared. Well, what was y squared again? It was a rightward facing opening parabola, negative y squared, leftward opening parabola, and plus 3 shifts it over to the right by 3. So this right here is that first function. Okay, let's make the first relation. The second relation right here, y equals x minus 1. Well, we know what that looks like, right? That's just the line y equals x, but shifted down by 1. The question is, where's that going to be? Is that going to be like right here? Where exactly is that going to be? I mean, we know where y equals x minus 1 intersects here and here, but we don't really know exactly where this intersection point is right now. We can find it pretty easily. Maybe we should go ahead and do that to make sure our graph looks correct. If x equals 0, if x equals 0 for this equation, what do we get? We get y squared is equal to 3, or y is equal to plus or minus the square roots of 3. All right, that's clearly bigger than 1, so this must be like negative square roots of 3 right here. So it makes sense that what we drew makes perfect sense. Now we found an area completely enclosed by these two graphs. So let's make it this yellow area. We want to find all of this. All right. Well, we could do this problem in terms of x dx, but if we do it in terms of y dy, it's one integral. If we do it in terms of x dx, it's two integrals. Can you see that? Let's just consider what happens if we tried to do this in terms of x dx. Ugh. We'd have to break it right here and then consider all the area on the left where the linear is above the quadratic, and we'd have to consider everything on the right where the quadratic is above itself. Whoa, can we even do that? I don't know that we can. So we're really forced into this whole y dy scenario. So let's do it. Let's just say, nope, we can't really track with that. So let's get this area under the curve using entirely y dy. That's pretty easy. Red function is on the top. I mean, it's to the right. That's kind of the equivalent of to the top, to the right. And the black function, linear, is to the left. Okay, so always right minus left. In these y dy problems, it's right minus left. Just like in the x dx problems, it was top minus bottom. Here it's right minus left. All right, let's do this thing then. Area under the curve. Area is going to equal the definite, maybe I'll change the color here so that it's easier to see. area is equal, definite from y equals something to y equals something. Ooh, we already know what those y limits of integration are. Do they? No, we do not know what the y limits of integration are. Okay, we can't count on that square roots of 3. That's not what we care about. We care about where these two graphs do what? Intersect. Look, there's an intersection point right here and an intersection point right here. Those are going to be at my corresponding y values. This one and this one right here. How are we going to find that? We need to know those limits of integration. Well, we need to set y equal to y, right? Oh, sorry, x equal to x so we can solve for our y values. So let's go ahead and do that. Let's set x equal to x. All right, we've got this first function is already in terms of x. The second function, if we want to make it in terms of x, what will it be? It'll be x equals y minus 1. No, y plus 1, isn't it? Sorry. X is equal to y plus 1. All right, so let's set these two functions equal. You got x is equal to 3 minus y squared. You got x is equal to y plus 1. Set x equal to together, which means you're setting 3 minus y squared equal to y plus 1. All right, looks like we're going to have a quadratic here in one variable. So let's go ahead and see what this looks like. Y squared plus y minus 2 is equal to 0. Is that right? Y squared plus y minus 2 is equal to 0. Yeah, does this thing factor? Sure it does. Y minus 1 y plus 2 is equal to 0. So that's y squared minus y plus 2y minus 2. Perfect. So y is going to equal negative 2 or 1, which makes sense. This looks like it could be negative 2, and this looks like it could be positive 1. So we're pretty happy with those limits of integration. We're going from negative 2 to 1. See that? Now let's get the colors back. Of what? F of y dy. It's really going to be call it x sub 2 minus x sub 1 dy. Right? It's going to be the right curve, which is our red curve, x sub 2, minus our black curve, x sub 1. Can you see that? The right curve is on, the red curve is in red, and the black curve is on the left. We're going to go right minus left. So this thing is a little more complex than we've seen in the past. Area is equal to definite integral from y equals negative 2 to y equals 1 of, well, what was x sub 2? What was the red curve again? 3 minus y squared. 3 minus y squared minus, what was x sub 1? Y plus 1, right? Now the whole thing needs to be in brackets and then dy. So we've got y limits of integration, y integrand, and y integral. Differential, sorry. All right, let's rewrite this and then we should be good to go. Definite integral from y equals negative 2 to y equals 1 of, this is 3 minus 1 is 2 minus y squared dy. Right on, integrate, you get antiderivative of 2 is 2y. Antiderivative of y is negative 1/2 y squared. Antiderivative of negative y squared is negative 1/3 y cubed. All evaluated from y equals negative 2 to y equals 1. All right, now I can certainly do this out by hand, but for my own speed here, what I'm going to do is put this into my calculator and give you an answer. All right, so according to my calculator, I'm getting 9 halves, of course, units squared. Very good. All right, folks, you are now off to doing lesson 67. That only took 20 minutes, so hopefully you've got plenty of time to work diligently on your homework. You must work on lesson 67 homework. If you're done with that, you can go on to lesson 68, but you must work on your math homework. Thank you very much, and I'll see you tomorrow.